Okay, good afternoon, everybody. So, hypothesis testing on means of multiple normal distribution, and the tool that we use is called analysis of variance, or ANOVA for short. And we had one example saying, for example, we have a process, and in this process we produce a grocery bag, and we want to see whether the hardwood concentration levels can affect or improve the tensile strength. Okay, so we have how many populations here in this example? We have 4 populations, which correspond to basically the levels of hardwood concentration, and we want to see if the mean of tensile strength produced by these 4 levels of hardwood concentration are equal or not. Okay, so as you can see, if it was only mu1 and mu2, then we would use 2 sample T. Okay, but it's more than that. It's more than 2 levels. And we had some terminology for that. For example, we said each population. Why this is acting up? Okay, so each population we also call the levels of the factor or treatments, and when we repeat experiments, as you can see, we call those repetitions replicates. We do it in a random order, and we want to evaluate this hypothesis test. We had some notations, for example, y j dot means, or y I dot means basically the summation of row I, and we can define also average for that row. Y dot dot means the grand total, and y bar dot dot means grand average. And we said the linear, the model, statistical model that you use is linear, and we say each observation is coming from its corresponding population mean plus some deviation or error. Each observation. What did you say? What did you ask? I'm sorry.
Sample mean or population mean?
Oh, that one is population. Okay, so the question is a sample mean or population mean. For now, it's population mean. The way that we build the model is based on population mean. The way that we estimate it is based on sample mean. Okay. And we know that each population mean can be written as basically the overall mean plus some deviation for each population. And this deviation is called, sometimes called treatment effect, or effect of each population, or deviation of each population. And if I combine these two, this is the statistical model I get. And then these are the assumptions that we are using. Epsilon ij's are normally distributed. Summation of tau i's are 0. And we assume that they are deterministic. And population have equal variances. This is similar to 2 sample T, if you remember. And we show that, okay, these 2 hypothesis tests are equivalent. We can either test whether mu's are the same, or we can test whether the tau's, or basically treatment effect, are 0. Okay? If tau's are 0, means that mu's are exactly the same. In this case, mu1, mu2, mu3, and mu4 are exactly on top of each other, equal to mu. Okay? Any questions so far? Yep.
Assumption about epsilon ij being a normally distributed
so
parameter.
Why do we have this assumption?
Isn't that the standard deviation of each point from its population mean?
Okay, so that epsilon ij is not a standard deviation. So epsilon ij, we assume it's NID, 0 sigma squared. So yij is mu I plus epsilon ij. It's not a standard deviation, it's deviation from mean. Okay, and we assume that this deviation follows a normal distribution. Why? because later on I can do some hypothesis testing based on that normality assumption. Okay? So this is something like this. Let's say you have a population. This is mu. Each observation that you have from this population is mu plus some deviation. This observation is mu plus this deviation. And this deviation could be either positive or negative. Okay? So we said how we can basically do this hypothesis testing. We use ANOVA, and ANOVA partitions the total variability into two parts. So what I mean by total variability, each observation minus overall mean, and we know that we don't have overall mean, so we need to estimate that. So overall means like put everything together, take a grand average. So deviation means this point minus this dashed line, this point minus this dashed line, this point minus this dashed line. This deviation is squared, add them up. It gives you the total variation. Okay? And this is a quantity or known equality that we use. So the grand average can be written as these two components. So this is called between group variation. This is called within group variation. So let's look at each component more closely. So let me see. This part means y bar I dot, which is the sample average of each population. That's estimate for what? That's an estimate for, let me see if you are following. Mu1, exactly. In this case is mu1. That's an estimate for mu1. This is an estimate for mu2, and so on and so forth. So what it says, each of this component minus the grand average, okay, squared, and add them up. So y bar 1 dot minus y bar dot dot squared. So it shows the difference of each mean from the overall mean. Okay? That's why we call it between group or between population variation. So the part of variation which is coming because of the difference between means. Okay? If I have overall variation here, some part of variation is because of difference in the means of populations. Okay? So that's one part. The whole thing is total. So the second part is each observation minus its corresponding mean. So in this case would be this blue dot minus corresponding mean, this blue dot corresponding mean, this blue dot corresponding mean, and so on and so forth. So what is this variation? Within population variation. Because each observation is compared with its corresponding mean. This red dot is compared with the red mean, and then we add them up. So what we are doing here, for each population, we find within variation. And how many populations do we have? 4 populations. We add them up. Does it make sense? So the second part is difference of each observation from its mean. So this is called SSW. This is called, SSB, or sum of a square of between. This is called SSW, sum of a square of within. Okay? They are relevant, exactly. So that's a very good question. The question is, are they related to tau and epsilon? So this guy is related to what? Tau, and this guy is related to epsilon. Okay? Why? Because tau is the difference between here, between mu and the grand average, and epsilon is the difference between each observation and its corresponding. Okay? Any questions? Okay. Now let me ask you a question. So I have this equality. Okay? So what happens when H null is true? In terms of size of this guy and size of this guy.
The first one's 0.
0 or very small. Okay? So if H null is true means what? All mu's are the same. So the variation caused by between population is going to be very small. Okay? In reality, it should be 0, but we have some random sampling. That's why we don't get 0. So this part should be small, and total variation should be very close to within variation. So what we can do, we can always compare SSP and SSW. If SSP is much larger than SSW, or if it is small, let's say, is much smaller than SSW, then we can say H null cannot be rejected. Does it make sense? Because mu's are the same. That's the idea behind ANOVA. So as you can see, we are using the variance components to test mean. Okay, that's why we call it analysis of variance. So again, if H null is true, then this part SSP are going to be very small. So what we want to do, compare SSP with SSW, or between variation with within variation. Any questions? Is it clear? Yes. So the question is if it is related to treatment or not. Yes, that between group variations is related to treatment effect, treatment effect. Okay? So tau i's. So if tau i's are 0, then this SSP should be very small. Not exactly 0, but very small. Why it's not 0? Because it's random sampling. It's not the whole population. Okay? And SST should be very close to SSW in that case. So that's why I can use some ratio of SSP and SSW to do my hypothesis testing. If this ratio is small, then H null cannot be rejected. Does it make sense? Yes, exactly. Yeah, they are the same. So that's basically back to this slide. So there is no treatment effect. This is basically H null is true. These two are equivalent. Any other questions? You good? Okay. Now, let's see who remembers the first part of the course. So I from 1 to A, J from 1 to N, Yij, Y dot dot squared. There's a summation there I just dropped. That summation. Plus summation over Ij, Yij, var bar I dot squared. Okay? Now, let me start with this guy. So first of all, let me divide everything by sigma squared. So what is sigma squared? We know that epsilon ij follows a normal distribution with this mean and this variance. Let me divide everything by sigma squared to scale them. Now, anybody can tell me what is the distribution of this guy? What? Chi-square? What is the degrees of freedom? Let's just start with this guy. So what is the distribution of this guy? chi-square with how many degrees of freedom? N minus 1. This is similar to this guy. So this is sort of n minus 1 s squared. Okay? So it's chi-square with n minus 1 degrees of freedom. Yeah, but exactly. How about this guy? This is chi-square with a times n minus 1 degrees of freedom. Why? Because we know that if we have independent chi-square, if we add them up, the result would be chi-squared with summation of degrees of freedom. So n minus 1 degrees of freedom, how many of them do we have? J is from 1 to A. I'm sorry. Let's call this one J. Let's call this one I. Is it I from 1 to N? 1 to A, exactly J from 1 to N. Yeah. So how many of them do we have? A. Okay? Okay, good. Okay, thank you. So that one is chi-squared with n minus 1, and then we add them up, chi-squared with a n minus 1. Okay. How about this guy? Let's see who can tell. Same thing?
It's another chi-squared, right?
It's another chi-squared, yes. But what is the degrees of freedom? What? Remember, this one you are subtracting the corresponding mu for each population. So this is a small one, because this small one, you can separate each population. Okay? So each population itself has a chi-square. But here you are subtracting from grand mean. So each individual has a chi-square. With how many degrees of freedom? 1 degrees of freedom. Okay? How many do I have overall? So it's basically chi-squared with a n minus 1 degrees of freedom. I'm losing 1 degrees of freedom because I'm estimating this guy. Okay? So the first part is chi-squared with this degrees of freedom. The last part is chi-squared with this guy. What is this guy? It's chi-squared with the difference of degrees of freedom, exactly. A n minus 1 minus a n a times n minus 1, which is chi-square with a n a minus 1, actually, if you do the math. Okay? So why this is true? Because we know that if I have the summation of two chi-square is going to be chi-square. If this is chi-square, this is chi-square, this should be also chi-square. Degrees of freedom is basically what happens. Okay? And this is true on the rich null, actually. Now, why I'm doing this? Because I can then find, so the distribution of the ratio. This is SST, sum square total. This is SS, what? Between. And this is SS within. Okay? Now, let's see. So SS between, so what we want to do, we want to find the ratio of SS between and SS within. The ratio of what? Two chi-squares. What is it? F. But not exactly. We should divide it by their corresponding degrees of freedom. Okay? So SS of between, what is the degrees of freedom? A minus 1. SS of between, what is the corresponding degrees of freedom? A times n minus 1. So this follows an F distribution. Why? Because this guy is chi squared with A minus degrees of freedom, and this guy is chi squared with A n minus degrees of freedom, n minus 1 degrees of freedom. So therefore, I get an F distribution with this 2 degrees of freedom. That's how I come up with my test statistics and critical region. Okay? Is it clear? Yes.
Multiply by the degrees of freedom, like the top and bottom by 1 over the degrees of freedom. So it's not really the ratio of just...
Yes, we are kind of, exactly. It's not exactly ratio, but the ratio, we don't know what the distribution is. So we are sort of like using some multipliers to make it some distribution that we know. So the question is why this is not exactly ratio, and I agree, this is not exactly ratio, but we are just multiplying by something to make it some distribution that we know. That's it. Okay? So we can call it like sort of a scaled ratio or normalized ratio, because we are normalizing with respect to their degrees of freedom. Any questions? So, is it clear? By the way, sometimes instead of using SS between, they use SS of treatment. Okay? That's another terminology. And instead of using SS within, they use SS error, sum of a square of error. So SS is sum of a square. Okay. Then, so what they call this guy mean square treatment. And this call mean square error, which follows an F distribution with A minus 1, A times n minus 1 degrees of freedom. So that's the definition of mean square. So you have something divided by degrees of freedom. We call it mean square of treatment. SS of error divided by degrees of freedom, mean square of error. That's it. So basically, the ratio of mean squares follows an F distribution. Okay? That's just a terminology. Any questions? Is it clear? So what should we do? Based on data, we can easily find SS of treatment, SS of error. We know what A and N are. Then we can find F naught and compare F naught with these thresholds. Actually, this threshold. If it is greater than this, we reject H null. Otherwise, we do not. So you can see there are two basically form of degrees of freedom. One is A times n minus 1. Another one is capital N. So capital N is total number of observations, which is this guy, or summation of Ni. Sometimes the number of experiments that you have for each level is not the same. Okay? In this case, your capital N is the summation of Ni. So total number of observations that you have. Does it make sense? Any questions? You good? Okay. So now how we can calculate sum of a square. I already gave you a couple of equations. Here. So these are the equations for SST, SSP, and SSW, or SS treatment and SS error. However, these are easier to calculate. This equation is easier to compute. Okay? So what it says, just find a square of each variable, then subtract this quantity and add them up. That's it. That's going to be your SS total. SS treatment, that's SS treatment. How about SS error? We know that summation of SS treatment, which is SSP, and SS error, which is SSW. This summation is sum of a square total. So if I know this and this, I can subtract and then get this guy. Okay? That's easy. And so usually we have a table, we call it analysis of variance table. And this is the table that you see. I think in the exam that would be something like that. So I give you data, I give you this table. Some of the basically elements of this table is missing. You need to fill it out. Okay? So basically treatment, there are three sources of variation. The variation because of treatment, because of error, and total. There are corresponding sum of a square, corresponding degrees of freedom. You divide SS treatment by degrees of freedom, you get mean square. You divide SS error by degrees of freedom, you get mean square error. And the ratio of these two mean squares are F0. You compare F0 with this threshold, then you decide to reject or do not reject H null. Okay? Any questions? So we have one basically example. So let me see. That's the same example like hardwood concentration. We want to see if the level of hardwood concentration would affect the tensile strength or not. So I'm going to use this equation and find SS total, SS treatment, and based on that find SSE and complete the ANOVA table. So let me start with SS total is the summation of Yij squared from I from 1 to 4 and J is 1 to 6. A is the number of level. In this case is what? Is 4. And N is the number of, A is the number of levels, which is 4. N is the number of replicates. In this case is 6 minus Y dot squared divided by capital N. And capital N in this case is 24, which is A times N. Okay, so based on this, as you can see, the first observation is 7. So 7 squared plus the second one, 8 squared, until the last one, which is 20 squared, minus Y dot dot. This is Y dot dot, which is the grand mean. Grand sum. 383 squared divided by 24. So this gives me 512.96. How about SS of treatment? It's I from 1 to 4. Yi dot squared divided by a small n and yi dot, y dot squared divided by n. I'm using that equation over there. So in this case is 60 squared. This is y. This is yi dot 60, 94, 102, 127. So squared until 1 to 7 squared divided by 6, which is n, minus y dot dot 383 squared divided by capital N 24 382.79. Okay. So what is the next step? SS of error, which is SS of total minus SS of treatment in this case is 512.96 minus 382.79, which gives us 130.17. Okay. Now I need to basically build my ANOVA table. So source of variation could be treatment, could be because of error, and total. Okay. I have sum of a square. In this case, sum of a square of treatment is 382.79. Sum of a square of error is 130.17. And sum of a square of total is 512.96. Then we have DOF, or degrees of freedom. For treatment is A minus 1. For this guy is A times N minus 1. Okay? And for this guy is A N minus 1. That's the table I'm trying to So A minus 1 in this case is A is 4, is 3. This guy would be 4 times 6 minus 1, which is 20. And altogether is 23. Okay? So how about mean square? So mean square is 382.79 divided by 3. In this case is 127.60. And in this case is 130.17 divided by 20, which is 6.51. So what is F0? Actually, I don't need mean square total. What is F0? It's 127.60 divided by this guy. Mean square treatment divided by mean square error. In this case, is 19.60. Okay? So this is F0. I should compare it with what? With F distribution, let's say, well, actually I dropped alpha here. So I need to compare it with F.05. Let's say alpha is 0.05. And the degrees of freedom is 3, which is A minus 1, and A times N minus 1, which is 20. From table, that number is 4.94. So this guy is greater than F0. Therefore, what? Reject H naught. Which means what? There is a difference between the mean of tensile strength when we use different hardwood concentration. Okay? Or hardwood concentration is an important factor for improving the tensile strength. Any questions?
Yeah. Was the alternative hypothesis two-sided in this case?
No, the alternative hypothesis is this is not true. So it could be, yeah, it's sort of two-sided, yes. Yes, exactly. Yes. That's why we use alpha, not alpha over 2. That's correct. But actually, it's a very good question. So I know that hardwood concentration is important. But which levels are different from others? So that's the next question. Okay, which one is better than the other one? Which one is different from other one? Okay, so that's basically the after ANOVA analysis that we need to do. You will see in this lecture as well. Are we good here? Any questions? Okay, so these are the equations for unbalanced experiment. By unbalanced, I mean the number of replications is different for each level. Okay, it's not 6, for example, here. Here is fixed, and it's equal to 6, but could be 6, 5, 4, 3, whatever. For each level could be different. Then you use this set of equations. So you replace n with what? N sub I. Okay? But the rest is the same. Now, can I do confidence interval for each population? These are the equations for confidence interval for the mean of each population. Okay? So as you can see, I'm using t distribution because I'm estimating the variance. But there is one difference. So this guy is the average for each population, which makes sense. The sample average of each population. This guy is the t alpha over 2 with the corresponding degrees of freedom. What is the degrees of freedom? A times n minus 1. And MSE, actually this is important. MSE is an unbiased estimator for sigma squared. Okay? Always this is true, no matter when H null is true or not. So whether mu's are different or not, MSE is an unbiased estimator for sigma squared. If you have two populations, do you know what MSE would be? Let me see who can answer this question. If you have two populations, what MSE would be? Yeah, definitely. But we are assuming that variances of both of them, you mean the sample variances of both samples? Yes. But how? You've seen this before. Is it? Yeah, pooled variance. So if you have two populations, MSE is exactly pooled variance. Okay? Yeah. That's why, you remember, for finding basically the confidence interval, we used to have like pooled variance and stuff. We are using the pooled variance here as well. Okay, so it's basically the estimate of the variance is this, and this is the degrees of freedom corresponding to estimate of the variance, and this is y bar. So let's see what is the confidence interval on the mean when hardwood level is 20%. Okay, so for that I need to find y bar of 20%. Let's see. If I go back, 20% is here. So y bar is 21.17. So y bar of, actually y bar 4 dots. Is it the last one? Yes. Which is 21.17. Okay. And we'll go back to the equation. So the equation says 21.17 plus minus t of 0.025. Let's say alpha is 0.05. And how many degrees of freedom? 20 degrees of freedom. Okay? Because a times n minus 1 is 20. I need to find my MSE. MSE is right here. 6.51 divided by n. In this case, n is 6. Then I can find the lower and upper bound. If I do that, the lower and upper bound is, see if I can find it. Actually, I don't have the exact values. Sorry. But you can calculate it. I thought I have. It's not cool. Yeah. Okay? So you can find the upper and lower confidence interval. Any questions? So, what if I want to find the difference of two levels? Then the confidence interval for that difference is this. Okay? That's the equation for confidence interval. Why this confidence interval is important? How I can use that confidence interval? Anybody can tell me? Exactly. So basically, the ANOVA analysis of variance tells me whether means are equal or not. Okay? But the question, if they are not, can you tell me which two are different? Okay? Which two populations are different? Then you can construct this confidence interval and see if 0 belongs to that confidence interval or not. If 0 belongs to that confidence interval, we can say these two populations are the same. Otherwise, these two populations are not the same. Does it make sense? Okay? So I give you a couple of minutes to work on that. Try to find the confidence interval for difference in the mean of 15% and 10%. And here is the data that you need. Let me write down the equation. Somewhere here, probably. So it's y bar I dot minus y bar j dot plus minus t alpha over 2 a times n minus 1 degrees of freedom MSE divided by 2n. Just want to make sure this is correct. Yeah. Yeah. Oh, 2 MSE, sorry. Yeah, because we have two populations, so it should be 2 MSE divided by n. Okay. So the question is, find the difference between 15 and 20%, or confidence interval for that difference. Anybody got any numbers? Lower bound, upper bound? Yeah. Yes, alpha is 0.05. Actually, let me give you that T. Let's see if I have it. I don't think I have it. Can I cheat a little bit? Do you have the notes for two populations? Just want to find. Yeah. So here is T distribution for 0.025. And 20 degrees of freedom. What is it? .086. Okay. Thank you. So no numbers? Nobody? What's it again? Minus 3 point. Minus 1.74. 4.4. Positive? So this is negative, this one is positive. Anybody else? Any other numbers? You got the same thing? But that's okay. Why I'm getting... So this is like 15 and 20, am I right? This is for 15 and 20? And 10, oh, okay. Yep, okay, no, that's correct, yeah. I was thinking, wow, why is it different? Okay, good. So 15 and 10. So it's y bar of, let's say, 15 is number 3 dot minus y bar of 2 dot. And in this case is basically 15 and 10 is 102 minus 94, and which is whatever. Oh, sorry. 17 minus 15.67. Yeah. So this number multiplied by plus minus T of 0.025 and 20 degrees of freedom, 2 MSE divided by N, which is 6. This number is 2.086, and it gives you for upper bound 4.406, and for the lower bound minus 1.739. Okay? So what is the conclusion? There is no significant difference between level 15 and 10. So there should be significant difference between other levels. How many pairwise comparison can we have? How many? 4 factorial is one answer. 6, which is what? 4 chose 2. Yes. So 6 basic combinations we can have. I think next class I'm going to talk about the method which consider all 6 combinations at the same time and tells you which one is different from others. So which 2 pair means are different from each other. Okay? Any questions? Have a good spring break.